Good day, this is the midterm project on about creating 5 Java programs that would be converted into assembly languages. Let's start on the first Java program. The first Java program is all about creating a character number structure. The question that we would need to do is write a Java program to display the following character rhombus structure. When we say rhombus, it means like a tilted square. A common way to visualize a rhombus is the shape of the diamond suit in a deck of playing cards. Now let's begin on breaking down this Java program into step by step. Remember that the program should generate a diamond pattern using letters starting with letter A. The user inputs a number and the program prints a symmetrical diamond with that many layers. First, we need a way to take input from the user. Java Scanner class helps with that, so we import it. Now we need to set up the program structure where every Java program needs a class and a main method. This is where the execution begins. Here our class is prog1 and the main is the starting point. We create the scanner object SC to read the keyboard input of the user. Then we ask the user for the number n, which determines the diamond size. For example, if n is equal to 3, the diamond will have 5 lines, since it's 2n minus 1, where we can see how we derive from that later on. After that, we set up 3 important variables. Count decides on how many letters appears in each row. Count 2 manages the leading spaces to center the diamond, and C starts at A and changes as we print letters. Now we are here at the main loop where we use it in building the diamond. Mm. This loop runs 2n minus 1 uh, times once for each line in the diamond. For example, n is equal to 3. It runs 5 times, lines 1 to line 5. Now on the second loop here, uh, which we need to print the leading spaces, before printing letters, we add spaces to center the diamond. The formula n minus count 2 adjust the spacing dynamically. For example, on line 1, I is equal to 1 and count 2 is equal to 1. So spaces is equal to 3 minus 1, which is equal to 2. On line 3, the middle spaces is equal to 3 minus 3 is equal to 0, which is the fully centered. Here is the if-else statement that we use on adjusting space counts for symmetry of the rhombus. This if-else ensures symmetry. Before the middle line, I is less than n, increase counts 2 to reduce the space. After the middle line, I is less than or I is greater than or equal than n, it decrease count 2 to add spaces back. Now, we're on the for loop of printing the letters. In here, we print letters in a pyramid shape. The first half of the line, J, is less than count divided by 2. Increment C means that when J is less than count divided by 2, it increments the letter that we will be printing. The else statement here, which is the second half, should be decrement the C, thus creates the mirrored effect in each line. Uh, Now, to keep the diamond symmetrical, we use also the if-else statement where we increase the count by 2 before middle. Example, uh, example is 1, it becomes 2, 3, and 3 becomes to 5 letters. After middle, it decreases the count by 2, 5 to 3, 3 to 1 letters. Then, we will also reset the C to A for each new line to produce letters from the start. Then, the system out print ln is then used after we finish printing the spaces and letters for a line and we move to the next line. and going back to the main loop. But I is now equal to 2. Now let's see the output the, that tries to print the diamond shape or the rhombus character rhombus structure. Here we inputted the number is equal to 5 and it prints a diamond shape here. Now we can see here the equivalent assembly code for creating a character rhombus structure. First, we need to program the setup and data definition. Uh, this is the dot model small and dot stock 100 each, where we reserve 256 bytes for the stock. Here in the data segment, we can see that we defined our diamond size, uh, where we store the number, the n is into 7 in the memory. Then the 2n define byte question mark where the question mark is means it is uninitialized. Then uh, the count tracks letters per line, count to manage the spaces and I counts the line. Now we will start the program and initialize it. Uh, First, we will load our data segment into the address and into the DS register. Then we calculate 2n by loading n into EL and adding it to itself, then store the result in 2n. Then we proceed on the main loop where we calculate the spaces needed. Uh, the n minus count 2 since CL is n. Then for example is the that example here is the for line 1 with n is equal to 7 and count 2 is equal to 1, it gives us the 6 pieces. Then we print the spaces by comparing CL to 0. If 0, we're done printing and we will go in the space done. But if not, we will proceed below. Since we are not done, we will go in the bias interrupt, 10 each function, tapos 0e. 0e each prints the space character. Then decrements our spaces, counter, and loops back until all the spaces are printed. If it is finished, um, we go on the space then loop. Uh, Here, this part shows that we adjust the count to control the spacing. Before the middle line I is less than n, we increase count to reduce the spaces. Uh, After the middle, we decrease it to add spaces back. Now we will print the characters. Here we prepared for character printing and we move count CX uh, for into C. We move the count into the CX. Then uh, we move it for the looping. Then we calculate the midpoint by shifting count right here. Or it means it divide by 2. After that, we reset our character counter CL and starts with A. Then we go now on the print cars loop. These first two lines here, we'll check if we've printed all characters for this line. After that, we will print the current characters using BIOS. If before midpoint here, if before we midpoint, we increment the character A to B to C. Then after midpoint, we decrement the character C to B to A. Then we will move to the next character. Uh, on the cars done, we will just add the letter count by increasing by 2. Then, before we will, yeah, we will just adjust the letter count by increasing by 2 before middle line and decrease by 2 after. Then we will then print carriage return and the line feed for the new line. After all that, we will increment line counter. Uh, and look back if more lines to print. We will then terminate the program after the main loop. Here, if all if all are satisfied, then we will then demonstrate the output for this assembly code. Um, just remember that we initialize n as 7, in which it will print the letter up to letter G. Let's try to emulate it. Let's run it. We will see here that it prints the A, ABA, ABCA, ABCD, and decreases here, and F here, and ABCDEFGF, and it will go back to ABCDEF DCBA. Now let's wait for it to be finished. Right, so we here see the character rhombus structure uh, to be made in this assembly machine. Now here is our second problem from the Java program. And the problem is all about creating a Pascal triangle the given uh, with a given number of rows based on the user. Uh, we should remember that a Pascal triangle is a triangular array of binomial coefficients where the logic is built using nested loops. In construction of Pascal triangle, we should remember that each element is equal to the sum of the two numbers immediately above it. We can base our references on this picture. So here we can see that on the first row, here, this is the zeroth row or the starting row. And in the first row, we can see that um, the here is the sum. Uh, we can calculate it by knowing the sum of this number here of the above on it. Like 0 plus 1 is equal to 1 and 1 plus 0 is 1. Here we can see that 0 plus 1, uh, 1 plus 1 is 2, 1 plus 0 is 1. Third row, same, just like here we do. The fourth row, also like that. Now we are trying to make it happen by the knowing that how many input number of rows based on the user. Now let's go here. First, we start by importing the scanner class to allow the user input from the console. Then we define the main class and the main method, which is the entry point of the program. Here we declared our variables. The no row is the number of rows. Uh, the Just the number of rows the user wants to print. Then C is used to calculate the coefficient in the Pascal triangle. Uh, BLK helps manage leading spaces for alignment, and uh, while I and J are the loop counters. Then the program prompts the user to input the number of rows. This value is stored in no rows. Here, using the scanner object in. Then this outer loop runs for each row from 0 to no row 1. Then we use from 0 to no row minus 1. Okay. Uh, then we use this loop to print the leading spaces as I increases. Here, as I increases the number of spaces before numbers decreases. That it ensures the triangle shape. Then this inner loop prints the binomial coefficient for each row. The the value then this inner loop prints the binomial coefficient for each row. Then the values are symmetric and calculated dynamically. Then this if else statement here shows that this is the key part of the program where the first number in every row is always 1. For other values, we calculate the binomial coefficient using the formula C is equal to C times I minus J plus 1 over J. Uh, this avoids using the factorials directly, and it is efficient. Then after we finish calculating, we will then proceed on printing each coefficient followed by a space. After all values in a row are printed, we will now move to the next line uh, and begin again on the main loop. Then let's run the program to see uh, the output of our project. Let's say we input the number of rows to 5. Uh, it displays now here the Pascal triangle that each element is equal to the sum of the two numbers immediately above it. Like for this example, uh, here in the first row, since this is the zeroth row, the first row here, that here we have a imaginary 0, 0 plus 1 is equal to 1 here, 1 plus 1 is equal to 2, and 1 plus 0 is equal to 1, and so forth. Now, let's go on the converted assembly program of the said Java program. Now we will start by explaining each line of this code to have a better understanding of how our program works in assembly language of microprocessor emulator. Now, first, we define a small memory model and allocate a 256 byte stack using that stack 100 each. Uh, in a data segment, no underscore row is initialized to 5, uh, which represents the number of rows. We also define variables for I, J, and C, just like in the Java version. Then NL holds the new line characters, the carriage return, and the line feed. Then we begin our program by initializing the data segment. We move the data segment into EX, then into the DX register. Now, this is the main loop. The main loop, we compare the I to no row. If they are equal, we jump to done to terminate. Uh, but if it is not done here, we are going to here if it is done. But if we are not done, then we will continue printing that row. Now we are here in the printing spaces, where we compute the number of leading spaces needed for the current row by subtracting I from no row. Then we will now go to the SPSLE, LP, or space loop, where this loop prints the spaces using bias interrupt intent. Uh, the function is 0 each, where each call prints one character, and then we use CL as the loop counter, um, where it decrements it until all spaces are printed. After that, we'll be printing numbers where we go to the call loop and we initialize C to 1 at the start of every row. Then we also reset J to 0 before entering the column loop. Then we go to the next call loop where we check if J has passed I. If it has, then it, uh, it jumps to end call here. Since the uh, it is it didn't not jump, then we will proceed here, where we will be displaying the uh, after finishing all loop, we will be displaying the coefficient uh, and the calculation. Here, we print a space, then convert the value uh, in C to an ASCII digit by adding 0, and print it. It only works for values 0 to 9, as we needed more multi-digit support and additional logic if we want it to add up from more. And then after that, we will calculate in this part the binomial coefficient calculation, where C is equal to C times I minus J and divided by J plus 1. Yeah. This is done manually with multiplication and division using registers. Uh, MUL pulls the result in EX, and div uses BL as the divisor. The result is stored back into C. Then we increment the J and repeat until all coefficients in the row are printed. After the calculations, we will go to the end call. Since we are done here, we will jump on the end call. Mm. In the end call loop, after finishing one row, we print a new line using carriage return and line feed, similar to how the system out print and here works in Java. Then we will proceed, increment I and return to the row loop to process the next row. Then after all is done, we will then terminate the program. Now let's see the emulate or the output of this program in assembly. Let's try by running it. We'll see that 1, 1, 1, 2, 1, 1, 3, 3, 1, 4, 6. Yeah. Remember that Rn here is equal to 5. So that's it for the problem number 2. Now, here is the third Java program, where the question is all about creating a Java program to insert an element into a specific position in an array. We should remember that it should shift the remaining elements to the right. Now, first, let's look at the program on the Java. First, we import the Java util arrays to use the arrays that to string for printing arrays easily. Then, we declare the public class named prog3 and the main method where the program execution starts. We initialize the integer array named myArray with 10 fixed values and declare the insertion position at index 2 and define new value as 5, which is the element we want to insert. Then we would uh, print the original array in a readable format using array to string. Now, to start, uh, the loop here starts from the last index, which is 9, and shifts each element to the right until the index position is reached. Uh, this ensures that there's a space to insert a new value, which is 5. Then we insert a new value to the desired index, which is the 2. We'll insert a 5 in the index position of 2, where this is the zeroth index first, and this is this part here, the part of the 56, is the index position 2. We will put the number 5 here and shift the 56 and the rest to the right. Now, uh, then we print the updated array with the new value inserted. Let's see. Let's try running it, and we can see here that the original array 25, 14, 56, 15, 36, 56, 77, 18, 29, 49. Then in the new array, we can see that in the index position 2, there is a new value, which is the number 5 that we want to enter here in the new array. And the uh, and the number here is being shifted to the right by 1. Now, let's go to the microprocessor assembly program of this Java program. Let's break down the assembly version for better understanding it. Now, again, we use the small memory model where code and data are in separate segments and allocate a 256 byte stack. We define a data segment with my array, which is the 10 byte array that representing the original set of integers like in the Java version, the index position, a constant EQU that defines where the new value will be inserted, and uh, which is the value 2. And the new value, the value 5, is to be inserted here. Uh, Now, this is the string constants for the messages. The original message printed before showing the original array, new message for printed before showing the updated array, and the comma space for printed between numbers in the array, except for the last one, after the last one. Now, execution begins at the start label. The program sets up the data segment by moving the address of the data at data into the EX and then copying it to the DS so that a variable like my array can be accessed. Then this prints the string original array using the US interrupt 21H, which displays the string. Then calls a procedure that prints all 10 elements of my array separated by commas. With, in the print array procedure, we first go here. So you call it print array here. In the print array, uh, we see that we initialize cx with 10, the number of elements in the array, and sets si, the index in the register to 0, since we XOR it. Then we would load the current array element into AL. Uh, we use the AEM, the uh, ASCII adjust after multiply, splits a value in AL uh, into tens and units. The result is is equal to 10 digits and EL in equals to units digit. Then we will convert both digits into ASCII by adding 30 each, since the ASCII value of 0. Then uh, use the tens digit in BH using DOS function 02 here, and prints the unit digit in BL. Then prepares to start shifting from the last index. Then CX is used for the loop counter. Uh, then uh, then it moves back here. The SI is the array index pointer starting from the last element. If SI current index is less than or equal to the insert position, the shifting is complete and we jump to shift done. But if not, then we would then copies the value at index SI minus 1 to index SI, then effectively shifting it rightward by one position. Then we would then decreases the index and repeats the loop until all required elements are shifted. Now, uh, since the shifting is done, then we will insert the new value, where the shift done loop places the new value 5 at index 2. Now that the space has been made, it will then print the new line uh, 0DH0AH followed by the message new array. Hmm, New array. Then calls again the print array procedure to show the updated array with the inserted value. Then it exits and terminates the program. Now let's see if it works. Let's try emulating it and run the program. We can see here the original array matches here, and we insert the new value on the index position 2 and 5, the new value here, and it works. Now, uh, the question for the fourth program is write a program to find the second smallest element in an array. Let's go see the program in Java. First, we input the arrays class, which provides the toString method used to print arrays in readable format. Then declares the main class, then the main method that serves as the entry point of the program. Then we initialize the array, my array, with integers on it. Then we would then print the array using the arrays toString, which returns a string representation of the array elements. Now we initialize the two variables, min and second min. Uh, this act of placeholder is to find the smallest and the second smallest values. Now in this loop, to find the second smallest number, we iterate through each element of the array. If the current array equals to the current minimum, update. Uh, we should update the second mean to that same value. Uh, but if the current element is less than the current mean, assign second mean is equal to mean, which is the current mean becomes the second mean. Then mean is equal to my array, the index, the new mean found. And but if the value isn't the smallest but is smaller than the second smallest, update second mean. Then outputs, outputs and prints the final result. The second lowest number is blank the second mean. Now let's try to run it. We can see here that the original numeric array is 1, 4, 0, 2, 7, and 3, which is the smallest lowest number is 0 and the second lowest number is 1. We can see here that it is 1 and it is correct. Now let's move on to the converted uh, assembly um, code coming from the Java program. Uh, Now here is the step-by-step analysis of the code for finding the second smallest number in the array. First, we define the small memory model and reserve 256 bytes of stack. Then we initialize the array, one that contains the 6 elements that is similar to the Java's array, but using unsigned bytes. And here the mean and second mean. That's set to 127 maximum possible byte as placeholder. And this is the message. That message prints the second lowest number is blank before the result. And the new line that holds the DOS style new line with dollars and a dollar sign for string termination. Now let's begin on the main code. Here on the main code, we should set up the data segment TS so variables can be accessed properly. Then initialize the index register SI to 0 by using the XOR. Then let's go to the new element. We would load the current array element into EL. Then if EL is equal mean, then skip. But if EL is less than mean, go to the new mean. And as if AL is less than second mean, go to the second set second. Uh, but here, let's go the skip update. In the skip update, we can see that uh, uh, the logic of skip update loop is we would continue to next element if no update is needed. Then in the new min loop, we stores the old min into the second min and updates min to the new smallest. Then in sets second min directly. Then lastly, it outputs the result in the done loop where it prints the message the second lowest number is and loads the result and calls the number printing routine. Then prints a new line and exits the program. Here is the procedure for comparing and for sign decimal. Then let's try to emulate it. Let's try by running it. We can see that the second lowest number is 1, where we can see here that the array is 1, 4, 0, 2, 7, and 3. The smallest or the lowest number is 0 and the second lowest number is the 1. Now, here is the lesson fifth question that we will try to solve and understand. Here we have a right Java program to separate even and odd numbers from a given array of integers. Then put all even numbers first and then odd numbers later on. Now let's start understanding it on the Java program first. Now we can see here that first we import arrays, so we can easily print arrays. Then defines the main method. And here we can see that this is where it starts the execution here. Then we create and initialize an integer array named nums with 10 values. Then we will then print the original array using array to that to string, which returns a nicely formatted string of array contents. After that, we will call a static method separate add even. Uh, with nums inside and which it passes the array inside to it. The method rearrange even numbers to the left and add to the right. Uh, Here we will go into the static in. Uh, in this method, the separate add even, we initialize the two pointers, where the first pointer is the left side starts at the beginning and the right side starts at the end. And the outer loop here runs until the two-pointer meet. Then move left side until it finds an odd number and it keeps moving the left side index forward as long as the current number is even. Then move right side until it finds an even number and uh, keeps moving right side index backward as long as the current number is odd. Then we will then swap if necessary if both pointers found a pair, or even on the right and on the left. Then swap them and move both pointers toward the center. After all that, we returns the modified array to the main method. Then we will then print the array after separating even and odd numbers. Let's see if it works. Let's try running the program and let's see the console. We can see on the console the original array is 20, 12, 23, 17, 7, 8, 10, 2, 1, 0. And we can see at the first part of the array, we can see the even numbers and the later on is the odd numbers. Now we are finished in the Java program. Now let's go uh, on the assembly code of the step problems. Now we see that the first we need to specify first is the memory model and the stack size. After that, we initialize uh, the data in the data segment where the nums, which is the arrays of 10 bytes, which only unsigned values due to limitation. Then count 10, which is the number of elements in the array, and message 1, which the message printed before showing the rearranged array. Then we will start on the code segment of the main program now. Now, first, we load the address of the data into the DS register to access data variable. Then sets up the SI, the left index, and DI, the right index, just like Java's left side and right side. Then uh, we are on the main partition loop that checks from left, then stops at odd. Uh, we will then loads the num si into el and al 1 to check if the number is odd or even. If it is zero, if it is even, it increments si. Then if odd, jump to the check right. In check right loop, you can see here, it checks from right and then stops at even. Uh, it loads the nums di into AL, and if it odds, continue decrementing di, and if it is even, jumps to do swap. Then in the do swap, uh, it shows that it exchange values at indices SI and DI using AL and AH. Uh, we can see here that then it moves the pointers towards the center after swapping. Then, after all that, we go to the done partition. In here, the done partition, uh, where we can see we print the string array after separation and prepares to print 10 array elements. And then calls the print num. Since we call the print num for each element in the array, in this subroutine called print num, it prints the byte in EL as decimal ASCII characters and initialize division by 10 to extract digits and uses CX to count digits, pushes on stack. And then we use the div loop to repeatedly divide the number by 10 and pushes each remainder digit on the stack. We would then print each digit that pops digit of the stack in correct order. Then convert the digit to ASCII and prints it. It then prints a space after each number and restores it registers and returns from the subroutine. Then after that, let's try to run it in here. We can see that the array after the separation. Let's remember first that the original array shows that it is 20, 12, 23, 17, 7, 8, 10, 2, 1, and 6. Now we can see here that the array after separation is the 12, 20, 12, 6, 2, 10, 8. Uh, on the first array, on the first part of the array is the even number, and the second part, which is the on here part, the odd number, which is the 7, 17, 1, and 23. That's all. Thank you.